Hi, and welcome back to the first session of the ViViMaT workshop. The second talk will be held by Gianpietro Moras, who is Deputy Head of the Multiscale Modeling and Tribio Simulation Group at the Fraunhofer Institute for Mechanics of Materials, the IWM in Freiburg in Germany, where he's been working for about 10 years now. He received a master's degree in materials engineering at the University of Trieste in Italy in 2004 and a PhD in physics from King's College in London in 2008, where he worked under the supervision of Alessandro De Vita. Before becoming deputy head of the group at Fraunhofer IWM in 2014, he held postdoctoral research positions at the Karlsruhe Institute of Technology with Peter Gumsch and the Fraunhofer IWM with Michael Moseler. His talk is about the in-situ formation of aromatic tribolayers for superlow friction. Gian, we're listening.
Hi, I'm Gianpietro and thanks for watching this video. First of all, thanks a lot to Stefan Eder and Carsten Gachot for giving me this opportunity to guide you through a pretty fascinating subject in tribology, which has to do with the relationship between nanoscale properties of materials and their macroscale friction properties. In particular, I would like to show you how the ability of carbon to form nanometer thick graphitic-like structures on the top of tribological surfaces like this you can see here can help dramatically improve friction in mechanical components. This work is a combination of atomic scale simulations performed at Fraunhofer IWM in Freiburg and of very fine experiments by our collaborators at Fraunhofer IWS in Dresden, at the École Centrale de Lyon and at the Austrian Center for Tribology. So in the last couple of years, we have been involved in several projects aimed at developing materials for super low friction in automotive parts, materials that can operate in bearings and seals for extreme environments, such as seawater, for example, and components that even have to work in dry or minimally lubricated conditions. In all these examples, the system finds itself pretty often on the left side of our Stryber curve, where the ratio between the film thickness, the lubricant film thickness, and the roughness of the surface is roughly lower than 1. And therefore we can expect solid contacts between the two surfaces. In this situation, usually friction is a problem and wear is also a problem. And there is a class of materials that in some situations work very well for these conditions, and I'm talking about hydrogen-free carbon films like diamond or tetrahedral amorphous carbon. Not only are these materials very hard and their mechanical properties is outstanding, and so they have a high wear resistance, but they also have surfaces that are chemically very stable, they can be made very smooth, and the system itself is very stiff. And these three conditions are necessary in order to achieve ultra-low or even super-low friction. We are talking here about friction coefficients of the order of 0.01. Here I listed on the left a few examples. You can find many more in the literature with this kind of coatings like TAC and nanocrystalline diamond were used in combination with oxygen-containing molecules such as water or glycerol or glycerol monooleate to achieve friction coefficients of the order of 0.01. And the first explanation proposed by many of these works about how these low friction properties come about can be understood in these terms. So if you add two diamond or TAC surfaces that approach each other, the termination has been removed by a wear event and we are in ultra-high vacuum, then there will be covalent bonds between the surfaces because there are dangling bonds on the surfaces. This would lead to cold welding and localized amorphization with a pretty high shear stress or friction coefficient. But if between the two surfaces we had, for example, water molecules, and this is a nice movie I borrowed from Clelia Righi, and you can find more details in this publication here. Well, if we had these water molecules, as you can see here, they would readily dissociate and deliver hydroxyl groups and hydrogen that passivate the dangling bonds, the carbon dangling bonds on the surfaces, and prevent the formation of covalent bonds across the interface, thus leading to very low friction coefficients. This is, however, not the only way we have to passivate a carbon surface. Another way is graphitization. If you think about the chemical stability of graphitic compounds or benzene, for example. And in this case, I'm not talking about the increase in number of sp2 hybrid atoms in general, which would be true also in this case of morphization, but this doesn't lead to low friction. I'm talking about, for example, experiments that were performed a couple of years ago by the group of Maria Isabelle de Barros-Boucher in Lyon, in which they were able to suggest that passivation can also be achieved through the formation of nanometer thick graphitic-like structures on carbon surfaces that are disordered and partially oxidized. So to try to shed some light on these two mechanisms, we started years ago performing quantum mechanical molecular dynamic simulations based on the tight binding technique, with which we can simulate hundreds of atoms for a few nanoseconds. And the usual simulation setup is two blocks of materials. In this case, this is a diamond 111 system, so two diamond 111 surfaces. We can apply a normal pressure, a sliding velocity, we can control the temperature of the system, and we can add any kind of lubricant molecules we want in between the two surfaces. Bear in mind that the pressure values you have to use in this kind of systems is not the macroscopic pressure you apply to your system, but is rather the peak pressure at asperity contacts that we usually get from quantum mechanics simulations using the experimental surface topographies. Well, we performed many of these simulations for an increasing number of water molecules between these two surfaces. And what we can do is we can plot the shear stress for sliding, or even the friction coefficients in some situations, as a function of the number of water molecules between the two surfaces. And what you can see is that all these red dots, they cluster in a few different regions. These two regions that have a very high shear stress are two regions in which cold welding between the surfaces happens, either by means of an amorphous region or by means of single ether groups. Then, as I told you before, if there is enough water to be able to passivate both surfaces, then the friction can be very low. Bear in mind that this is a logarithmic scale, so friction here can be of the order of 0.02. If there is more water than needed to passivate the surfaces, then we will also find a nanometer thick water layer between the two passivated surfaces, and this usually gives rise to a slightly increased friction. But what is very interesting in this plot is this region here, because despite the low number of water molecules between the surfaces, we were able to achieve very low friction coefficients. And to understand how this comes about, you can have a look at this movie here, in which we had 3 molecules between the two surfaces. At the beginning, you have a cold welding situation mediated by ether groups, and as the simulation goes, you can see the extraction of carbon atoms from the upper surface. You can see that these atoms pull on the carbon atoms of the lower surface, and suddenly you will see the appearance of an ordered structure here on the top layer made of pentagons and heptagons that suddenly doesn't require any kind of chemical termination anymore, and the friction is very low, the termination is stable. Even if you press with about 50 gigapascal, this surface remains stable. This shouldn't come as a surprise, as for very low coverage of hydrogen atoms or other passivating species, the lowest energy reconstruction of the C11 surface is the Panday reconstruction that is made by this kind of zigzag chains that are pi bonded and are aromatic and very chemically stable. So we have a case in which we were able to observe that an aromatic structure on diamond surface can lead to very low friction coefficients. However, this is true for the 111 diamond surface, but not necessarily for other surfaces that don't have such kind of aromatic reconstructions. Usually, however, we know that in tribological conditions especially, diamond films are covered by a few tens of nanometers of amorphous carbon. And so in order to simulate a generic carbon diamond surface, what you can do is start from the amorphized version of the previous simulation. And to simulate the releasing and forming of asperity-asperity contacts in periodic boundary conditions, what we can do is every now and then we can pull the two surfaces apart. We can add water molecules to mimic that water enters the contact. We can press again and slide again. So, as you will expect, the simulation starts with a very high shear stress. As we continue adding water and hydrogen, there will be chemical mixing of oxygen and hydrogen in the amorphous region, and suddenly the friction drops to the usual value of 0.02. And this happens when the lower surface is basically passivated by some disordered structures made of pentagons and hexagons that are aromatic. So if this is true for an amorphized diamond surface, it should hold true for tetrahedral amorphous carbon. And we know that this water and glycerol, for example, work in this sense for tetrahedral amorphous carbon. And this is the next simulation I'm going to show you, in which with the usual simulation setup, we placed a glycerol molecule in between the two surfaces. The glycerol molecule can react with the two surfaces by using these hydroxyl groups, and it can cross-link the tribological gap. Upon shearing, the molecule gets basically destroyed by mechanochemically, and it releases carbon, these green spheres, oxygen, the red spheres, and hydrogen, the blue spheres, to the surfaces. This happens with a rather high shear stress, and as the simulation goes on, we will see the formation of an amorphous region that contains oxygen and hydrogen, and occasionally you will see the formation of large voids. What the system is doing in this case is looking for an interface with low shear stress for sliding. And if you bear with me for some seconds, you will see that the system will be able to find such interface here in this region, and as soon as that happens, you see it here, you will see that the covalent bonds between the upper and lower part of the system will decrease, and suddenly the friction will drop to the usual 0.02 value, and this happens when both surfaces are basically passivated by an aromatic dome-shaped structure, and you can see from below and remove all the atoms in the bulk, and you will see this kind of pretty ordered structures with some oxygen passivation somewhere. This, of course, we have seen this for water, for glycerol. What about other molecules that contain oxygen? And we know from all the experiments from Kano and co-workers that this can work on TSC using molecules such as glycerol monooleate as well. This is the esterification process, product of glycerol and oleic acid, and it has many of these reactive sites, such as this ester group, the carbon-carbon double bonds, and the OH groups. In order to rationalize these results of Kano, we decided to perform experiments on simpler versions of the molecules, which we use on the between TAC surfaces. And we start by using octadecane surface, fully passivated. Then we add a carboxylic group, and we have stearic acid. We add a double bond, we have alaidic acid. In the other conformation, this is oleic acid, and then we use glycerol. And in all these cases, we perform experiments in boundary lubrication. What happens is that, just look at this plot here in the middle, is that the friction coefficient decreases as we increase the number of reactive sites. And only molecules with more than two, or at least two reactive sites, can achieve friction coefficients below 0.02. So in order to understand what's going on here, we performed also in this case tight binding simulations. And I summarize here the results, and what we see is that molecules with only one reactive site, they tend, at least at reasonable pressure values, to react with only one surface. So they anchor on one of the two surfaces. But if you have two reactive sites, you can easily react with two surfaces simultaneously, and you obtain this cross-linked configuration. If you apply a tribological load to the system, you will see that the molecules get stretched, and they can release oxygen, hydrogen and carbon atoms to the surface. And this proceeds in the same way we have seen for glycerol, the formation of an amorphous region and then at the end the passivation of the surface either by hydrogen and oxygen or with aromatic structures. If you look at the critical pressure you need to achieve this necessary cross-linking state, what you will see in the simulation is these red bars, and you will see that the only systems that can achieve this cross-linking state for reasonable pressure values of 5 gigapascal, which is about the maximum pressure value we have in our contact, are those with more than one reactive centers. For all other molecules, you have to press way more than the pressure value we have in the contact. And if the correlation with the friction results is pretty good, I would say. So this convinced us that there is a large class of molecules containing oxygen and hydrogen, maybe also other elements we don't know yet, that can lead to this aromatization process. And the next question is, do we actually need the carbon coating, or would it be sufficient if we had molecules that can form a carbon film on other kind of surfaces? And this is the case of our last simulation I want to show you, which is pretty much work in progress, in which we did perform the same kind of simulations between two silicon nitride surfaces. We sandwich a few glycerol molecules, and what you see as the simulation goes on is that you will see the reaction of glycerol with silicon nitride, the formation of nitrogen-containing molecules, the oxidations of silicon atoms, and also the formation of cyclic species containing nitrogen and carbon. Our colleague in Lyon, they performed the experiments on this system. Actually, they did it before we did the simulation, and they achieve actually in this kind of glycerol-lubricated silicon nitride system friction coefficients that are below 0.01. And if you look at the XPX spectra, you can see that inside the wear scar you have the appearance of carbon-nitrogen and carbon-carbon double bonds that weren't there before sliding. Even more interesting, if you use isotopically labeled glycerol that has C13 instead of C12, and by the way gives the same friction coefficient and same XPS spectra, and you can have a look at the map, the TOF-SIMS map of the species formed on the surface, you will see that within the wear scar there are many CN related species that contain C13. So there is a reaction between glycerol and nitrogen in the surface, and there is even a signal for C6 rings. But if you are able to etch the surface, just the first nanometer of the surface, you will see that this signal becomes weaker. This is an indication that the tribo film formed by glycerol on nitrogen can be very thin, nanometers thin. And if you look at the lubricant after sliding the glycerol with mass spectroscopy, you will be able to find the cyclic species containing hydrogen, carbon and nitrogen as those we can see here in our simulations. So we hope this is also a case in which we can show that surface aromatization is important for friction of a large class of hard coatings, not only carbon coatings. And with this thought, I would like to thank you very much for your attention. If you have questions, please post them in the comment sections here below. I will be more than happy to answer them on the 3rd of December. Bye-bye and have a good day.
Hey, thank you very much, Gian, for your presentation. And to all you viewers, if you have any questions or comments, please leave them in the comment section underneath the video so Gianpietro can prepare some answers that are going to be streamed live at our Q&A session on December 3rd, 1600 Central European Time. See you there!